Okay, we ran out of time again, so here we are, part 3 of the video. So you should have watched the previous 2 parts called indirect addressing. And while I was away, after I paused for a few minutes there, I noticed a little mistake on our copy table function here. We're using the LPM instruction copying the value that the Z register is pointing to into temp, storing it in the SRAM, which is where the X register is pointing to. Then we're comparing the low bytes, comparing with carry the high byte. If we're not done yet, meaning our compares are not equal, so the Z bit will not be set, then we need to go back and do the next byte on the copy table function. If we are done, we just need to return. So what we can do is BRNE is go from there to copy table to get the next byte. So instead of doing it, I'm going to stop this simulation here. Okay. So I'm going to change this name to copy table. And then just delete the next line here. And we shouldn't even need this one. So let's try this. So I'm going to assemble this again. Okay, and it completed. Now we'll simulate this part. So let's go to debug mode, and I'm going to step down through to here, RAM end. Now we have our registers, and if we look at our 26 to 31, that's registers X, LNH, Y, LNH, Z, LNH. So Z, LNH, let's see what we get put in there. So ZH is 7F, and that's going to point near the end of our table, near the end of the flash memory. X, L, and H should be 0, 1, 10. So we had a 10 byte offset, 10 hex byte, so 16 byte offset from the beginning of the SRAM. The SRAM starts at 0, 100. The Y needs to point to the end of the table, so that's going to be 7F something. Let me see. So Y, oh, hold on, we have an issue here. Oh, notice I forgot to shift my address to the left. So I got to stop because it came out 3F and it should have been 7F. We needed to double this word address to make it a byte address. So when we do a comparison with Z, they are equal when it gets to the end of the table. So doubling it, we can shift it left once and that doubles it. So that should work there. And so I built it again and stepping through the simulation again. So we have all of our values now in our X, Y, and Z register. And okay, now we're going to call the copy table function. And so that's going to put the current address. Notice the current address is the program counter address is 3E right now, right? So it's going to put that on the stack when we do the rcall instruction. So we'll go ahead and look at the stack while we're here. So you remember where the stack is on RAM end, right? So we'll go to the data memory to look at our RAM, SRAM memory, and we'll go to the end. Right now it's a 0, 0. So when we do the next step, it's going to put the address of the next instruction, which is this NOP instruction, on the stack. And there it is, 3F. So it was 3E the program counter. Now it put 3F on the stack. So when it comes back, it's going to come back to that NOP instruction at the beginning of main. So now we're going to go through, do the LPM. We want to look at R16 temp to make sure we get the value 1D in R16. So we have 0F in R16. What happened to our 1D? Okay. All right, let's go a few steps and see what's happening here. So I'm going to go back to the beginning of the data memory. That's where our X register is pointing to. So it's going to store the 0F at the SRAM start plus 10 hex. So it shows there is a correct address location. I just haven't figured out yet why it's a 0F and not a 1D. Because table address, table end. A 0F is an indication, if you look at the program memory, these are all FFs, right? Table ADDR4, table ADDR4. Okay, I'm gonna Okay, I found the problem. Up here, notice I put a 2 here instead of a 1. That was a typo apparently. So I'm going to stop the simulation and build it again and run it again, and we'll just step down through quickly because we've already done this. Okay, now we're back where we were. And hopefully we get a 1D now. And we did. So R16 temp has a 1D now. And then it's going to store that 1D into our data memory. So we'll go back to the data memory. And store it at 0110. So it did. Hex. And compare with carry. So the Z bit's not set, which indicates they're not equal. And so now we're going to go back to the copy table, get the next value, which is a 1E, and you can see the 1E in temp, and then it's going to store that into the next value in there. So we're in a loop now. It does 1E, and then it's going to do a 1D again. And so we're basically at the top of the, which essentially is a cosine function wave, which is adding the maximum value to the sine wave because we're at the very beginning of the sine wave on the highest rising amount. So I'm going to auto step this, and we have a breakpoint already set, so it'll come back to main. So this is going to copy 200 values, so it's going to take a few seconds, several seconds to do that. Right now it's got 32 values. Okay, this, maybe I'll skip ahead in the recording a little here. Yeah. Okay, so it copied the entire table, and it finished nicely when it got to the end. So our BRNE copy table did as it should. When it got to the end of the table, the comparison resulted in a Z-bit set in the status register, which you can see is still set. So when it did the BRNE, it was not equal to, it was equal to, so it didn't do the branch, and it returned back to main. So the table copy function works fine. So we use the X register as a pointer for storing the command. We use the Z register with the LPM command, and the Y register we used as a 16-bit address to compare with the Z register. We could have used any other pair of registers instead of the Y register, but it was there and handy. And it already has named registers YH and YL, just like ZH, ZL, XH, XL have. So that made it convenient. So now we're going to end this one before we run out of time, maybe. And we're going to write a function that configures the stack pointer on the next video, and then read the data from the stack pointer, or excuse me, from our memory every 20 milliseconds, and then update the stack pointer value by adding these values in this table to the stack pointer. Oh, excuse me, adding these values. Why am I doing the stack pointer? Okay. We're going to be reading this table and adding the values from this table to the OCR register. There we go. And that OCR register will control the pulse width, and that will control the servo, so it will sweep back and forth in a sinusoidal fashion. So when it gets to the end of the travel, it'll slow down, and then it'll speed up and go in the other direction, and then it slows down at the other end, so it makes a nice smooth sweep motion on it. Okay? So we'll end this video here, and then we're going to come back and I'll probably configure the or set up the timer 1 to do, which we've already done. So I'm just going to go ahead and set it up because we've already covered all that part. But then we'll go ahead and write a function in the recording that will read the value every 20 milliseconds and update the OCR-B register to update the pulse width on the servo. Okay, so thank you for watching, and stay tuned for the next video. We'll be back.